Hi, my name is Mike Aguilar. I'm here from Sandia National Laboratories. I've been working with Jim Brandt, Dr. Ben Allen, and Dr. Douglas Pace. Today, I will be just going through and talking about our new method for describing and retrieving information on InfiniBand fabric congestion research, and that's something that we've been working on. We'll be talking about motivation, goals, related work, approach, initial results, and then finishing up with future work and conclusions. We want to be able to improve computational efficiency by improving high-speed network performance. InfiniBand is a shared high-speed network resource that is commonly used in HPC systems. Unfortunately, much of the network has been hidden from our view. So, we would like to be able to develop a more complete understanding of what is happening at the InfiniBand switches. We want to understand what causes congestion, how long it lasts, and when it starts and stops. We want to be able to identify factors that might cause congestion, and then hopefully mitigate that congestion by maybe localizing data transfers, maybe using virtual lane quality of service, and then maybe combining applications that are more data intensive with applications that are less network data intensive. Congestion-related information that we are interested in are pieces of information that tell us about what links are backing up with data, otherwise known as back pressure. When data is having to travel over several switches to get from a source to a drain, and when an application is naturally data intensive, and then when we also have uneven traffic flow from an application that might be doing more data transfers from certain nodes than others. And then also another issue for us is we want to be able to see when information might be dropped across a link for some weird reason. We've found the current monitoring tools to be inadequate to lift the veil off the internal InfiniBand network to the point of allowing us to more clearly see network congestion. And then take that information and match it up to other information sources from an HPC system that we might have. For instance, some monitoring systems provide information on job-based view. Some have a very wide window of information data gathering, and even more importantly to us, we want to be able to, if we're trying to match information up from different sources, we want to know when we got that information. So we want to timestamp. We want not only to be able to acquire a full set of regular information metrics, but we also want to know when that happened. Nice thing is, OpenFabrics has provided us with management data metrics that provide us switchboard information. Thank you, Ira and other people. We want to get that management data metric information. We want to know both the regular and extended management data metrics. And we want to be able to sample that synchronously at a tight interval. And most importantly, get that timestamp. LDMS is a monitoring framework that we've been using, and sysclass IB is a plugin that is used to gather the metrics from local HCAs. It has both timestamps, provides a tight window that we like, and can be used to gather both the regular and extended data management data metrics. There is one issue with sysclass IB, It only gathers the metrics from the edges of the network, so the switches are still hidden from us. We can see the data coming in and out of different compute nodes, but we can't see how it's getting conveyed over to the other compute node, and if there's a congestion on the switch ports in between, we don't know where that is or how it happens. So basically, our research is working to extend the sys class IB capabilities to allow us to gather metrics from the internal switchboards. So the first question is, if we're doing synchronous data gathering and we're doing it at a tight window, is that negatively creating issues with our computation performance for our applications, otherwise known as jitter. And LDMS is being used on some very large systems. Blue Waters is a 28,000 node system with 8,000 LDMS daemons running it all at the same time. And we've run that system and seen no performance hits with our computations. It's also, LDMS is also being used in Trinity. If you have any questions about jitter, Jim had presented a paper at Supercomputing SC15 a couple of years ago dealing with that information. Distribution of our data gathering is built right into LDMS and right into sysclass IB. So we can distribute the load of gathering our metadata metrics from across the system into smaller daemons. So everybody's doing a little bit of work and the whole gets the information. And then also, even better, is the fact that with our, the way that we're gathering our metrics, we can actually put daemons closer to switches that might be of interest to us. So there's less traversal of data gathering. And our new sampler extension is called IBE Fabric. So we want to be able to gather a target set of metrics, metadata metrics from our collectors. We want to be able to identify the LIN port that we want our sampler to, our metric gathering to get off the switch. And we want to be able to know who we are connected to when we get that information. And then even more importantly, we want a timestamp so we can correlate different runs from different applications and any other information we would get from other different types of information that we're getting. We're getting our queries over VL15, which is the typical MAD metrics. And then we're also using LiveNet Discover to acquire the topology. The brains between our new IBE Fabric sampler plugin is actually the Delegator. The Delegator discovers the topology and then allows the user to input information on maybe the hardware of the fabric. It allows the user to input preferred metrics, and then also maybe lids and ports that are close by the sampler. And maybe also a subset of MAD metrics that you might want to, let's say you want to drill down, something that you might be interested in, to a subset. The Delegator is multi-threaded. The reason being is we're hopefully going to scale this up on very large systems. And so we're assuming that with all the plugins, IBE Fabric plugins coming up all at the same time, that we need to be able to support that. It uses a local attached ACA to the fabric, and then uses the libraries LiveNet Discover, LiveMad, and LiveIBMad. So what happens if you don't input specific information to the to the Delegator. The Delegator goes out and acquires a topology of the network fabric, and it can evenly distribute the number of lids and ports to the samplers on the network. And it will also pick a full set of metrics, so instead of drilling down, you can get all the metrics. And then also, it determines whether the ports also can handle extended metrics. Choice of metrics include traffic volume, congestion, and maybe link errors, the remote connections, so you can check both ends of the link. We can see if all our transmitted data matches all the received data, and then port information, etc. Congestion metrics that we're interested in are transmit weights and back pressure. Another one that might be interesting to us are VL15 drops. That would cause us to think that maybe the information we're getting back is suspect. We aren't currently providing anything beyond the normal metrics and the extended metrics. So things like omnipath additional metrics or Feckin and Beckon are not being utilized right now. And then currently, our Delegator only supports homogeneous network fabrics, though later on we're talking about and discussing extending the Delegator to work with heterogeneous network environments. So on all your systems, you might have a Mellanox connected to a QLogic or whatever. So the IBE Fabric plugin uses a local HCA to go out and make requests to the switch processors. Uses libmad and libibumad. And the daemons from IBE Fabric will start up a communication to the Delegator. It will send out a component identifier, and then it'll gather the information on what lids and ports it's going to sample off of what switches. From the Delegator. And then it'll use that information and report it back to an LDMS monitoring aggregator. The aggregator will take all the information from each daemon, integrate it together into one set, and then allows a set to be stored off in a large disk array or whatever. Again, the daemons that we're using for the sampling are distributed across the fabric and across the system. That does two things for us. It keeps the load down on the system. It also allows us to put those samplers closer to the switches that we're wanting to gather information from. So if a compute node is connected to a switch, it goes out and can acquire the switches that information from without having to traverse a large distance, which kind of comes in handy. The other aspect of the sampler is that it is synchronous, like I said. So everything is getting sampled at a certain time interval that's fixed. And we use some underlying libraries to do that. I'm going to skip all this because we've already talked about it. So this is actual output from our IBE Fabric plugin on LDMS. And you'll see that we have a timestamp. You'll also see that we have a duration of sampling time. That helps us out to know what our window is if we want to increase our sampling, for instance, to get a more fine-grained sampling window. And then also gives us a list of how many metrics that we're getting back on each sample. The actual one thing about the Delegator is that if it's evenly distributing the number of metrics and lids and ports, it'll actually, our size of metric retrieval will be variable. It's dynamic based on what your input is, what the topology looks like, and what were requirements for the, maybe our input file is for the sampler itself. The metric output is, again, we want to be able to see who's got what metric. So the first two items on the left will tell you the lid and the port. For instance, this would be lid 22, port 6. And it'll also break it down to the MAD metric. For instance, port transmit data, port transmit weight, receive data, receive packets, transmit weights, etc. Our sampler passes on the lid port as the connecting lid port that we're working with. So if we're getting for instance, we're sampling one lid and port on a switch, we can see who it's connected to on the other end. And that allows us to make sure, hey, we can correlate things, see if we're getting the right number of receives and transmits on both ends. And if we're dropping, for instance, a link might be an issue or something, we can be able to see that. And then it allows us to help us see what the topology looks like and where our data flow looks like. So we did a lot of experiments with the test bed system. We haven't scaled it up yet to our full systems. We did locally connected sampler to a switch, or maybe a couple of them in this case. We wanted to see what the time was for getting that information, and we also distributed it across the network. So in another case, what we did was we took our samplers and said, well, okay, we sampled the local switch. How is it going to work if we go across the network to a remote switch, or maybe to a core switch? And the results were that we had some waiting. Most of our processing time for the metric gathering was waiting on the processor inside the switch. So we would, for instance, we'd make a request, and those requests have to wait on a single-threaded processor within the switch. It's usually a small one. So a good chunk of our time was just waiting on that to respond. We found that with one port, one switch, it was a small amount of time, about 100 microseconds. It would scale up. 4 would be 400 microseconds, for instance. 8 would be 800 microseconds. We did find on our small test bed system that our expectation was that it would be an even climb as far as time, but we found that that wasn't the case. When we started sampling 8 ports or 16 ports, our time was still less than what we expected it to be. And that could be because we have only 8 connections to each switch. We don't know yet. Again, we haven't scaled it up yet, so. One thing we also checked was to see, again, we wanted to see if there was a problem with jitter. On our test bed system, I ran a lot of test jobs, different scenarios, mostly all MPI traffic, all gathers, reduces, all reduces, etc. And again, we didn't see any performance hit. Again, looking at a large number of different test jobs at different lengths and stuff. Currently, if we have a sampler that goes down, we lose metric gathering. Or if, for instance, a sampler doesn't come up, we don't get that information at this time. We want to be able to later on be able to have the delegator redistribute that responsibility to other samplers that are working, and we haven't got that working yet. And also, we would like to be able to start working with OmniPath in the same scenario too. So we do have a new measurement tool that helps us reveal congestion on InfiniBand networks, demonstrates low overhead. We know that now. Again, further testing will prove it again, but we've already run LDMS on very large systems, so we're not expecting anything. And then it reveals directly previously inaccessible data switch behavior, and then does so in a way that we can, with a timestamp and with fixed time synchronization. So when we go later on to analyze issues possibly, or make some decisions on how we're doing mitigation for congestion, we can correlate things with the other system information. And thank you for allowing me to speak with you today. Is there any questions?
Yeah, have you thought about using the perf manager or console, which sits on the box that the SM runs, so that you don't have to send all those queries over the net?
Yes, we've looked at perf manager. The problem with perf manager is it requires a very large window of time to gather back the metric data from across the network. And then also, we're not getting a timestamp. When we request data out of the IBE Fabric sampler, we're requesting it with a timestamp on it, so that when we go back later, we're able to, like I said, correlate that data with other monitoring information.
What are you using to synchronize? Is it NTP, PTP? How much resolution do you need on your synchronized clock?
Well, it's around a second, or up to 10 seconds in a lot of cases, and I'm trying to think of the library name.
So is that sufficient? Are you able to see what you want to see with that coarse grain?
Yes.
Okay.
Yeah.
We're synchronizing using, so we're waking up on libEvent events that are scheduled according to the host's idea of time, and they're using NTP. So.
So with the data and stuff you've collected so far, what have you done with it? I mean, you've decided, oh, that's too much load for this machine, or oh, we've had malfunctioning hardware we didn't know about, or what is it that you found out with this tool?
Oh, right now we're running it on a test bed system, so we haven't scaled it up. We've done just pretty much a proof of concept. We are planning on scaling it up to bigger machines, and then hopefully we're going to get information that'll allow us to first find out what causes congestion and then mitigate it, and we'll be able to make some more educated decisions on what we're going to do after we get that information.
Well, since you've said that the overhead is low, I guess you're intending to do this on, live big runs, right? Eventually,
yeah.
Right? Okay.
Yes, so we haven't done the InfiniBand networks yet, but we have done analysis looking at congestion, regions of congestion, how large they grow, how long they live, et cetera, on, for instance, the Blue Waters Gemini network, and also on Trinity. And so the idea was to extend that kind of work to InfiniBand networks.